All right, welcome everybody to our chapter on gases. Today I'm going to go over sections 1 through 3 via lecture, and then I'm going to film a video on some practice problems later for us to talk about how to do our pressure conversions as well. All right, so let's go ahead and get started. There isn't a ton to go over to start with. First thing we're going to cover is just what exactly pressure is. Pressure is defined as the force that is applied to a specific area. On Earth, we use atmospheric pressure, which is the weight of an air column that is approximately 1 meter squared, and how much that air weighs from the surface of the Earth all the way up to the edge of the atmosphere. And that weight is typically referred to as the amount of pressure in that specific unit of area. So we call it atmospheric pressure, or ATM. From there, we can talk about different units of pressure. There are quite a few discussed. And like I said, we'll practice some conversions with these different units of pressure here in the near future. The first is the Pascal. And Pascal is probably one of the more scientific-based units as far as SI units are concerned. Now the scientific community pretty much always accepts ATM as the SI unit of pressure, but before that it was the Pascal, because it is calculated as a Newton per meter squared. So this is like a finite physics-based concept. The other type of another unit that is kind of outdated but is still kind of seen once in a while is the bar of pressure. A bar of pressure is a scaled up unit of pascals. So it's a lot of pascals in one bar of pressure. A lot of units that exist for pressure involve whether or not they are useful on a day-to-day scale, or if they're useful in like another planet scale and things of that nature, or if they're useful in like different parts of our planet, like underneath the ground and or on the planet, on like the surface of the sun, things like that. So we had to have units that can scale well, instead of trying to use prefixes for every little thing. That being said, one of the more common units of pressure that is still used today is millimeters of mercury, also known as torr. They are approximately equal to each other, and 760 torr is 1 atmosphere of pressure. And this is one that we talked about a little bit with lab when we did that earlier. Today, because I am filming this on Thursday night. And when it comes down to it, this is measured using a barometer. In front of you, you see a pressure-based barometer that when the atmosphere of whatever environment this barometer is placed in pushes down on the mercury column then rises in response or lowers in response to whatever pressure is actually being exerted on the mercury surface. And then what we do is we measure the height of that mercury column. Now, if it's at 760 torr, which is really close to what we would see at sea level, we would also say it's in 1 atmosphere. From there, we can talk about how pressures of gases have been measured using a manometer, which again uses a mercury substance in a tube that is connected to a closed container in order to measure just the pressure of this gas. We basically modify the barometer we saw earlier from letting atmospheric pressure or atmospheric air push down on this column of mercury to allowing it to be a reaction gas or a reaction vessel that pushes down on this particular mercury. Again, we measure the difference in the height between the two sides, and we say that the pressure of the gas then is going to be the atmospheric pressure and the height combined. And this is a very old school way of measuring pressure. Now we have really fancy devices that we can attach, say here on a vessel, and it'll just tell us what the pressure is. In fact, when we get to our next lab with gases, we will be using one of those fancy devices, and they're like Vernier Lab Pros. So they will measure pressure based on the response to a detector. Next thing that we just want to make sure we understand is how pressures work on the planet, because that's where we do our chemistry, and we call those standard pressures. These are pressures that are measured specifically at sea level. If you're not at sea level, things change very slightly. We are slightly above sea level, and you saw that when I gave you today's pressure that we were a little bit higher than 1 ATM. We were at like 1.008 ATM because we are just slightly above standard sea level, and so our standard pressure is just slightly elevated. The further up above sea level you get, the more your pressure changes, and we just want to make sure we understand at this point the conversions or what the equalities are for pressure units. Again, in front of you, you see the most common ones that we are going to deal with, and that is the atmospheres of pressure, the torr, and then the millimeters of mercury, which are equal to each other. So 1 torr equals 1 millimeter of mercury. And then, of course, the very last one, which is the kilopascal, a very physics-based unit. And since a lot of chemistry is physics-based, you'll see this used sometimes in various classes. Whoops. And then from there, we're going to move into the basic laws that were discovered and or that explain relationships between variables like pressure, volume, and temperature, and number of moles or amount of gas. The first that we want to discuss, of course, is Boyle's law, which relates pressure and volume at constant temperature. And so one of the things that we can note, and of course this is a Charles Boyle experiment, is that when volume is being manipulated at constant temperature, it will vary inversely to pressure. So as volume goes up, pressure goes down. As volume goes down, pressure goes up. We say they're inversely proportional, and then what we graph is the thing on the left. So if we see an inverse proportion, we're going to see this weird looking curve that kind of goes down as you get further and further up on the pressure scale. If we then graph velocity versus the inverse of pressure, we get a straight line. And so with the different gas laws, we're always going to look to get a straight line by graphing either direct relations. So you see a direct relation here. Since this direct relation did not come out as a linear one, we took it and we then plotted this so that we could get a linear relationship. Then we move into Charles' law. Charles was a man who studied the volume and its relation to temperature while pressure is held constant. And so if we think about pressure being held constant, we can think about how a balloon that is already tied has a constant pressure, but its volume can still change. And you've seen this when you've seen a balloon deflate over time. A helium balloon that loses its air is a slightly different concept, but I digress. When we graph volume versus time, we find that they are directly proportional. So no need to graph inverse. As volume goes up, temperature increases. All right, last law that gets us to the last law that we're going to cover is Avogadro's law, and this will lead us into the ideal gas law. Avogadro's law relates volume and number of moles and states that a volume is going to be directly proportional to the number of moles. So as you increase the amount of gas that you have present, the volume should also increase. Hopefully this makes sense to you on a logical level, in that if we keep adding more and more of something to a container that can change size, the size will in fact change. Think blowing up the helium balloon, and how much of the helium gas gets added is directly proportional to how large the balloon gets. All right, so I'm going to stop lecture here for now, and then like I said, I'm going to film a separate video involving pressure conversions.